An analytical study and review of open source chatbot framework, RASA. Abstract: in the era of chatbots, besides imitating humans, they can also perform complex tasks like booking tickets for movie, etc. Out of various implementations, RASA is open source implementation for NLU and DIET model. It can interact with database, API, conversational flow, interactive learning with reinforcement neural network. In this study, various features of RASA core are studied, and up to much extent it can perform complex tasks. Implementation details are studied, like interaction with database, API. Tracker store has been examined with modifying the socket.io core file, adding metadata to the user message data, so that user IP and port can be captured. Furthermore, the action, interactive learning and implementation details are tested on Windows Pycharm IDE. Keywords: chatbot, RASA, open source, NLP. Introduction. RASA conversational AI assistant is quite different than earlier traditional FAQ interactions, as it is based on natural conversations, means like how humans interact with each other by considering what earlier the context was sent and what actions are to be taken in reference to the contexts, and gracefully handling the unexpected conversation and driving the conversation when the user drifts from normal conversation path, and also improve over time. Thus it's far beyond the FAQ interactions. RASA conversational AI assistant normally consists of two components, and they are RASA NLU and RASA core. RASA NLU can be just treated like ear, which is taking inputs from user, and RASA core is just like the brain, which will take decisions based on user input. 2. Recent work. Chatbots are software that behaves like human, answering the question which are asked nowadays. Development in this field going to scale up. Now chatbots not only answer simple questions but can perform complex tasks like fetching the results from API, booking tickets, and various management tasks. For the development of a chatbot, it requires a team of many experts, but to overcome the scarcity of time and resources, reuse of open source software is done. In this paper, 1, Boklisk, T. et al. Introduced the RASA NLU and core for the first time with open source license. The aim of this study was to provide a dialogue system based on machine learning and understanding the language to the enthusiast or no such expert in technology. The package 2 they developed was of minimal size, and advancement is done in the package. With the efforts of 344 contributors, 244 releases of RASA have been released with total of 18,023 commits. In his work 3, Lacerda used the core of RASA and presented a new software stack called as RASA PTBR, boilerplate for the non-specialist who doesn't much about the internals of the chatbot, considering the chatbot as black box. Now, chatbots are intelligent systems which can perform complex tasks and has many application in robotics and natural language processing. In the recent time, there is development in the field of artificial intelligence, so the chatbots are acting as customer service agents. In this study 4, Jiao designed a functional framework which implements the principle of RASA NLU, and furthermore he integrated the RASA NLU with the neural network methods, resulting into an entity extraction system, and later on recognizes the intents and related entities. This study showed that neural network outperforms in with RASA NLU. In the study 5, RASA chatbot is compared with Microsoft Bot, RASA, and Google Dialogflow, and the various performance metrics have been tested. The extensibility and open source license makes RASA more versatile than other enterprise softwares. This paper examines 6 the available technologies and implemented the use case prototype to give up insight that chatbot can be used with social networks so that smart chat system can be employed. In the study 7, a social chatbot for the football has been designed which answer the questions to the Spanish Football League. Chatbot is deployed with Slack client, having text-based interaction. It extracts the information about football players, team, and their trainers. 3. Flowchart. 1. The message from the end user is fed to the RASA NLU interpreter, whose output is structured output containing the original text, the intent, and entities if any, shown in Fig. Architecture. Fig. 1. RASA architecture flow chart. 2. The tracker maintains the conversation state and receives the structured output from interpreter. 3. The output from tracker fed to the policy, which acts on the current state of tracker. 4. The policy decides which appropriate next action is to be performed. 5. The log of selected action is maintained by tracker. 6. The appropriate response is provided to the user, using intents defined in NLU.md, like utter_response. 4 Features. A. Policies. The class RASA.core.policies.policy decides what action is to be taken during each conversation steps with bot. There are many training policies in RASA core like memoization policy, mapping policy, keras policy, TED policy, embedding policy, form policy, fallback policy, and two-stage fallback policy. For obtaining best results and performance of our model, these policies should be used in combination. These policies are configured in config.yml. 2 parameters max_history and data augmentation affect the performance of models, so they need to be set up considering performance. The execution of the policy will be based on the priority, highest priority policy will be executed first and so on. Priority is calculated on the basis of confidence score of each policy, which having higher score given higher priority. The default policies are 5 Form policy, 4 Fallback policy and 2-stage fallback policy, 3 Memoization policy and augmented memoization policy, 2 Mapping policy, 1 TED policy, embedding policy, keras policy, and sklearn policy. If mapping policy and memoization policy predict the next action with same confidence score, then the action related to memoization policy will be executed provided other parameters remain same. B. Slots. To fill the forms, the entity's value to be retained in the memory. They can store the values which are supplied by user. Slots can be of text, float, boolean, categorical and unfeaturist. Based on type of entity, they are used in different scenarios. C. Forms. It is analogous to web forms, but they are filled by bot from the inputs of user. If a user wants to ask for restaurant search from chatbot assistant, and in response to that our assistant wants to avail information like type of food, number of people, seating arrangement, etc. So here comes the need of forms and policy defined for this forms policy, which is having highest priority as per the RASA. Form name to be defined in domain.yml as forms, restaurant_form. D. Interactive supervised learning. To improve the efficiency of bot, by learning called supervised reinforcement learning. In which the bot action predicted based on confidence score, we can change the predicted intent action to guide the bot. In the URL localhost 5006 web link, we can see the states of the dialog flow, and we can proceed for the intended dialog. New stories are generated as the dialog flow is modified, so they are generated automatically by interactive mode of RASA. Live stream, RASA plus Bot Society integration launch, December 13th. Fig 2. States of the chatbot with supervised learning. eTracker store. It is just like a kind of storage which will keep record of all the conversations with the chatbot in your database. There are many tracker stores provided by RASA core like in-memory tracker store, default, SQL tracker store, Redis tracker store, Mongo tracker store, custom tracker store. If we restart the RASA core, entire history data in memory will be lost. This is the reason we are not using in-memory tracker store. Depending upon the database you have, accordingly tracker store can be used. The entries of endpoints.yml are shown below. Action_endpoint, URL, localhost 5055 web link tracker_store, type, SQL dialect, PostgreSQL hashtag the dialect used to interact with the DB URL, 127.0.0.1 hashtag, optional, host of the SQL DB, e.g. localhost port, 5432 DB, RASA_func hashtag path to your DB username, Postgres hashtag username used for authentication password, Postgres hashtag password used for authentication query, hashtag optional dictionary to be added as a query string to the connection URL. V procedure to maintain custom logs. If a client/customer wants to connect RASA core, there is some requirement of network service to be used by client/customer, and some protocols are also required like HTTP protocol, WebSocket, etc. In addition to this, for interaction of client with RASA core, open port must be allotted to the individual client. To achieve this interaction with RASA core, a different mechanism is required by client. So how a RASA core process will communicate with network? The answer is provided by socketto.py, which will serve the purpose here. In nutshell, the socketto.py will provide the inter-process communication between core and network socket, and providing unique identification based on sender ID to all the clients who are interacting with core simultaneously, and thus maintaining their states. Here we have captured only remote_address and remote_port, but we can gather much more information also. Fig 3. Schematic diagram of working of socketto.py. A modification of socketto.py. In the socketto.py there is a class named socketio input channel. We have taken two more members of class, and these are client_IP and client_port, and at the time of connection when the bot receives messages, values were assigned by environ remote_address and environ remote_port in the connection method. Async def connect, SID, text environ, -none. Async def handle _message, SID, text, data, dict, -any. Metadata equals client_IP_address self.client_IP, client_port, self.client_port. Message equals user message, data message output_channel sender_ID input_channel equals self.name, metadata equals metadata. Thus when the connection established with client, the table events in RASA_func database of pgadmin4 will have the metadata entry under column data. The table events have 7 fields and can be observed in Fig. And the metadata in data field look like this. Event, user, timestamp, 158808620.2976427, metadata, client_IP_address, 127.0.0.1, client_port, 0, text, hello, parse_data, intent, name, greet, confidence, 0.9857399463653653564, entities, intent_ranking, name, greet, confidence, 0.9857399463653653564, name, inform, confidence, 0.0035573919303715323, name, request_restaurant, confidence, 0.0023641688749194145, name, bot_challenge, confidence, 0.0021205565426498665, name. Affirm, confidence, 0.0019410221138969064, name. Stop, confidence, 0.0015613293508067727, name. Thank you, confidence, 0.0015150005929172004, name. Deny, confidence, 0.0009625948732718825, name. Chit chat, confidence, 0.00023804804829106666148, text, hello, input_channel, socketio, message_ID, ABF0CC8D44014C9D95 at 043D0A6D9. 6. Integrating with API and database. When query or data is received by RASA from the end user, RASA will predict the values of entities and intents from the message. All this handling is done by RASA NLU unit. RASA NLU. Intent, get_available_tickets. Intent is classified from the message, and RASA stack will act on the action that is defined in the domain.yml. Based on this action, request will be done to the defined API in action.py, to get the updates requested by the user. After this, RASA core tries to predict what to do next. This decision will be based on various learning paradigms and dialog flow in the stories.yml. Defining actions. Intent is classified from the message, and RASA stack will act on the action that is defined in the domain.yml. Based on this action, request will be done to the defined API in action.py, to get the updates requested by the user. After this, RASA core tries to predict what to do next. This decision will be based on various learning paradigms and dialog flow in the stories.yml. As the work of the action is based upon requirements, here we assume fetching data from API. A GET request is sent to the API, and RASA action class will work on the response received from the API. Based on the response code, processing on the response can be done to provide the expected result to the user. Class API tickets action. Def name, self. Return ticket action. Def run, self, dispatcher, tracker, domain. Res equals requests.get, API underscore URL plus destination plus, API key equals plus API underscore key. If res.status underscore code equals 200. Data equals res.json, records. Out underscore message equals buses available for the destination :n1. Format, data destination comma. Dispatcher.utter underscore message, out underscore message. Out underscore message equals .format, data buses. Dispatcher.utter underscore message, out underscore message. Return. B configuration with database. Based on the database like Postgres, Oracle etc. required Python dependencies need to be installed, like for Postgres pcog2 is the driver adapter. Its configuration is defined in endpoints.yml. Fig 6. Database adapter driver configuration in endpoints.yml. The data needed to be fetched from the database. This processing can be done in defined action as explained above. An instance of connection on which cursor is defined, is used to execute the SQL query. Based on the result from database, the response is given to end user. 7. Conclusion and future scope. From the study it is concluded that RASA core features like slots, forms, supervised interactive learning, API integration, and database makes it a complete framework that can be used to perform highly complex tasks. The chatbot based on RASA has more capabilities than any open source alternative. Further, in this paper, internals of RASA has been modified to carry out custom data logging of client IP and port. All internals and custom action has been studied, which further states that RASA is a complete open source framework for the development of chatbots and for the developers who don't want to dig into the internals of natural language processing. The future scope of the study, voice and face recognition engines can be integrated for more complex tasks like ATM cash withdrawal. Performance may be enhanced with use of various learning procedures of machine learning.